Hello. So I'm going to interrupt all the marine reptiles to talk to you about snakes and trees. This project is part of my PhD. And one of the main hypotheses that I wanted to look at is whether large-scale events, such as mass extinctions and rapid climate change, have affected the evolutionary histories of squamates. And in this particular project, I'm looking at snakes and the Cretaceous-Paleogene mass extinction. Before I get to all my trees, a very simple one. Snakes can be divided into two main groups, Scolopophidians and Allithinophidians. Scolopophidians are much less diverse and much less morphologically disparate. And that's because Scolopophidians are very much adapted to a fossorial lifestyle, such as this Typhlops. They like burrowing, eating termite eggs or other things they can find in the ground. In contrast, Allithinophidians represent almost all modern snake diversity that we know of, with over 3,000 species. They do fun stuff like become marine or largely marine, terrestrial, arboreal, and in my opinion, are very cool to look at. So whilst we have all this modern diversity, the snake fossil record is a bit more patchy, as one would expect from vertebrates. We do have some beautiful skeletons. However, a significant amount of the data is just vertebrae, and that's because vertebrae have a much better fossilization potential because the snake skull is just so slender. And the vertebrae present some problems. First of all, lots of homoplastic characters, which make them really difficult to use for phylogenetic reconstructions. And if you leave them out, you're missing out a lot of snake diversity. So what we decided to do was largely use molecular data. I subsampled a matrix from Zheng and Wiens for 115 snake taxa. It was important for us to use a lot of outgroup taxa because this allowed us to use more calibration points. So with 42 calibration points, we're using about 4 times as many as most squamate analyses tend to use. I did phylogenetic I built my first tree in Firebase, and then did divergence time estimation both in Firebase and Pamel, so using both Bayesian inference and maximum likelihood. The reason we started in Firebase was because it allows us to use the CAT GTR model, which using simulations has been shown to be very good for data sets like this. In contrast, Pamel allows you to play around with your data a lot better, and whilst divergence time estimation in Firebase for me was taking about 2 months, Pamel was taking 1 to 3 weeks, so that was a massive step up. And then today I also want to present some preliminary data on ancestral state reconstruction in R, doing stochastic character mapping in PhyTools. So we started out by building a tree, and we're pretty happy to find that at the base of Allithinophidia, which are the black ones, we find these really short branch lengths, which we thought might correlate to rapid rates of evolution and potentially a bit of a radiation. In contrast, Scolopophidians, the fossorial ones, seem to be evolving much more slowly at a leisurely pace. So the first main output from Firebase we got was, luckily, showing this beautiful radiation around the KPG. The blue bars represent 95% confidence intervals, and what that means is we can't say with certainty that this divergence is actually happening after the KPG, but it certainly supports our hypothesis. And a lot of analyses might have stopped there, but we really wanted to be sure that we were recovering a signal for a radiation and not just some lucky coincidence between the models we were using and our data. So we started to do more testing in Pamel. In these graphs, both the X and Y axes represent one analysis, and the dots represent the mean estimates, the bars 95% confidence intervals, and if you can spot them, I've labeled the KPG nodes in red. And if both analyses recover very similar dates, then we would expect all these dots to fall along the diagonal line. So as you can see here, the unpartitioned data set on the y-axis compared to the partitioned data set came up with slightly older ages. So this is not as perfect news, but it basically relates to the partitioned data set being used as a way to emulate the cat part of the modeling that we used in Firebase, which has been shown in simulations to be superior to not having the cat part. And so we've continued with the partitioned data set rather than the unpartitioned data set. Next, we also looked at different clock rates, so independent and autocorrelated clock rates. We did this both in Pamel and Firebase, and each time the results came out largely congruent. As you can see here, the red dots are very nicely close to the dashed lines, which represent the KPG, and they're also much better following the diagonal line. Finally, I wanted to play around with priors on calibrations, because having so many calibrations obviously has a large effect on these divergence time estimations. And the two I'm showing here are skew normal on the y-axis and skew t on the x-axis. And the difference between them is where they put the majority of the weight. So with my 42 calibration points, I have a lot of minimum dates and maximum dates. And what skew t does, as you can see here, the minimum being here, is it puts a lot of weight very close to the minimum bound, whereas skew normal spreads it out a bit more. So skew t basically emulates us having very strong confidence in the fossil calibrations that we're using, that they're actually extremely close to the node that we're calibrating, whereas skew normal allows a bit more leeway. And as you can see, these two correlate very nicely, and the KPG nodes all have their confidence intervals over the KPG. So I also started recently doing some ancestral state reconstruction. And first I started by just subdividing snakes into terrestrial, freshwater, marine, or freshwater and marine. And this came out with a really nice, strong signal for terrestriality. As you can see, all Scolopophidians are terrestrial because they're all fossorial, and terrestriality as a general term is also very widespread in the Alethinophidians. I've also done some analyses where I split up terrestrial into the categories it should actually be, which is arboreal, semi-arboreal, terrestrial, semi-fossorial, and fossorial. But as you can imagine, adding that many categories suddenly makes the signal a lot less clear. And it became extremely dependent on what model I was using to reconstruct this data set. So if you have any insights on how to get around these problems, I'd be really keen to chat to you later. Another thing that's really interesting about lizards and snakes is that they are known to be extremely good at changing how they reproduce. And snakes can be both oviparous, ovoviviparous, and viviparous. And there's also several groups of several snakes which can do parthenogenesis. And I thought this would be interesting to test just as an aside. Little did I expect to get a signal that potentially what is happening at the KPG is that Alethinophidians, in black, are starting to experiment with viviparity in an environment that wouldn't have been particularly friendly to snakes, and potentially with a lot of temperature changing and a lot of predation, it would have probably been good to just give birth, have your young be able to fend for themselves straight away, rather than having to put them down and sort of hope for the best whilst they lay in the ground. So in conclusion, both Bayesian inference and maximum likelihood support evidence for an Alethinophidian radiation at the KPG. And this pattern is resistant to some tampering with the modeling, both with relaxed clock models and different priors. And it is possible that post-Cretaceous Paleogene snakes started exploring with viviparity and terrestriality. And I'd like to thank my supervisors, my office, and the various people who've helped me both do our work and actually given me computer access. Thank you.